Good morning. Now, I sent you a message over the weekend and I said I would spend the first part of this lecture covering the essential features of workshop 2. Now, I realize that some of these points might have not got across during the workshop, and that's partly because of the problems that we're having delivering face-to-face teaching and online teaching at the same time. But I assure you, we are solving these problems. This week, I promise you, this week the workshop will be QR code. There's a QR code. There's a link to the QR code. I promise you that the workshop this Friday will go smoothly. Okay, now the workshop on last Friday, we were covering workshop 2, and workshop 2 is the question about food, which is the question we're talking about throughout the lecture notes. It's this question here in which we have a sample of 8 households. For each household, we observed weekly income and weekly expenditure on food. And we have to do a scatter plot, and we have to get the regression estimates. We have to draw a fitted line through the scatter. We have to get the residuals. We have to get the standard errors. And then we have to do various tests of whether food is a normal good and whether food is a necessity and so on. Get a 95% confidence interval, do a prediction, get an estimate of the income elasticity, and then consider whether Engel's law holds or not. The solution was given to you on Friday. If you were at the workshop, you would have got this hard copy of the solution. If you were not there, then it's on the Blackboard site. It's a 2-page document. On one side, we have the numbers, and on the other side, we have the answers to the question. Okay, so the way I've done this is I use the first table to work out the estimates. So first of all, you copy down the 2 columns, and then you work out the 2 means, x bar, y bar. Then you work out these 3 new variables, and you have to sum these 2 columns and then take the ratio of those to get the estimate of the intercept. The estimate of the slope. The ratio of those 2 numbers is the estimate of the slope. Once you've worked out the slope, you use the means again together with that slope to work out the intercept. Then you've got the fitted line. Then you can use another table, or you can use the same table if your writing is very small. First, you copy down the x variable and you plug in the x values into the fitted line to get y hat, which is the predicted values of y. And then you can copy down the y column again, and then you work out the residual. The residual is y minus y hat, and the residual is called u hat. Then you work out the squared residual, u hat squared, and then you find the residual sum of squares, which is the sum of those numbers there. Residual sum of squares is 586. And then you work out the standard error of the regression. Now, all we're doing here is we're using the formulae that are on the formula sheet. And the intention was to use a calculator to do this. Okay, now you've got another opportunity to do all this week, because workshop 3 is similar to this, but it's a different application. So workshop 3, this week's work, so please do it between now and Friday. Bring your answer on Friday, and we'll give you something like this, which gives you the answer to workshop 3. Once you've worked out the sigma hat, which is the standard error of the regression, then you use 2 further formulae to work out the standard error of the slope estimate and the standard error of the intercept estimate, and they're given here. Over the page, we've got the answer. There's a positive relationship between the 2 variables. As x rises, y also rises. This is describing the scatter plot, which I haven't drawn here, but it doesn't matter. You've seen it before. And then the fitted regression line. Well, here we're just putting the intercept. Well, it's just that equation again. Y hat. Fitted regression lines, y hat equals the intercept estimate plus the slope estimate times x. What's the interpretation of the 2 numbers appearing in this equation, when income is 0, expenditure on food is predicted to be £18.50. That's the interpretation of the intercept. When you interpret an intercept, all you're doing is you're predicting the dependent variable in a situation in which the explanatory variables, or explanatory variable in this case, is 0. If all the explanatory variables are 0, what do we predict y to be? In this case, when income is 0, we predict food expenditure to be £18.50 per week. If income rises by £1, food expenditure is predicted to rise by 14 pence. That's the slope. That's the slope estimate. Economists call this line an Engel curve. It's an Engel curve because it's named after the first economist who looked at household survey data back in the middle of the 19th century. Which household has the highest positive residual? Well, the residuals are here. Which one has the highest positive residual? It's that one there. The second last household, household G, has a residual of plus 10.5. This household spends £10.50 more on food than our model predicts a household with that income level to spend. So basically that household spends more than we expect them to. The household before them, this household here, spends less than we expect them to. So that's the interpretation of the residual. How far the observation deviates from the expectation. E, part E, is the good normal or inferior? Well, we have a prior belief that food is a normal good. We have a prior belief that as the household income rises, they spend more on food. So we have a prior belief that the slope is positive. So we set up a hypothesis test based on that prior belief. And the alternative is a one-sided alternative. B2 is positive. And we do a t-test, which is the estimate divided by the standard error, and we get 4.59, and that's the t-statistic. And then we use this reasoning here that I've explained in lectures, that this thing here has a t-distribution, a t6 distribution, because it's n-2 under the null hypothesis. And because we're using a one-tailed greater than test, we reject the null hypothesis in favor of the alternative if we're in the upper tail of the t6 distribution. And the upper tail starts there, and I've explained that in lectures, and we get this number from tables. So our t-statistic is 4.59. Our t-statistic is all the way over here. So it is in the upper tail. So we reject the null in favor of the alternative, and we say we have evidence that food is a normal good. Is food a necessity or a luxury? Well, remember what we're doing here. We're asking, what is the intercept? Is the intercept positive or 0 or negative? If the intercept's positive, it means the good is a necessity, because it means that it's a good that you consume even when your income is 0. We have a prior belief, again, that food is a necessity, so that's why we do a one-tailed greater than test. Estimate divided by standard error, 2.036. Again, we reject. We reject because 2.036 is bigger than 1.94. We conclude there is evidence that food is a necessity. And that's one way of looking at Engel's law. Engel's law, remember, which I told you what it was in the first lecture, Engel's law says that when income rises, food expenditure rises, but less than proportionally to the income rise. So, for example, if income rises by 10%, food expenditure rises by 6%, less than the proportional rise in income. Well, that happens if the intercept is positive. If the intercept is positive, Engel's law holds. If the intercept is negative, then that means the good is a luxury, and Engel's law does not hold. Anyway, confidence interval is the next question. You can work out a confidence interval as the point estimate plus or minus the t-value, but this time we're using two-tailed p-value. So you're looking in a different column of the t-table. This point's been explained in lectures as well. Critical value from tables times the standard error. 0.14 is the point estimate plus or minus the critical value from tables times the, point estimate plus or minus critical value from tables times the standard error equals point estimate plus or minus number. Work out those numbers and you've got a lower and upper bound to the confidence interval. The interpretation of the confidence interval is we are 95% confident that the true value of the slope is between those two numbers. Now, those two numbers, the whole range, the whole confidence interval is positive. That's a bit like saying we reject the hypothesis that the slope equals 0 in favor of the alternative that it's positive. If your confidence interval is completely positive, then that's like saying you've got evidence that the estimate is positive. So the confidence interval is closely related to the t-test that we did here. It's closely related, but not the same. And then you can do a prediction. The prediction is for a household with income 225, you just put 225 into the fitted line and you get 50. That's their predicted food expenditure. And then to get the income elasticity is dy by dx, the expenditure by the income, times x over y. Remember, this is what you need to do to get an elasticity. dy by dx is going to be 0.14. That's just the slope of the line. But to make it an elasticity, you need to multiply by the thing on the bottom and divide by the thing on the top. And I'm going to explain that in lectures shortly. dy by dx is beta 2, the slope, x over y. And for a given value of x, it can be estimated as the estimate of the slope, which we have, 0.14, times the value of x, whatever that is, and put y hat here, the predicted value of y. Well, we've already worked out the predicted value of y when x is 225. So when x is 225, the income elasticity is 0.14 times 225 over 50, which is 0.63. That means food is income inelastic because 0.63 is less than 1. Now, there's a little problem here, and that's that you haven't got a single number for elasticity. This is for a household with income 225. If we had a household with a different income, they would have a different elasticity. Now, that's not very good. If you're interested in the elasticity, then you just want one number which tells you what the elasticity is, and that's why if you use a different model, if you find log of y and log of x and do a regression of log y on log x, then the slope in that regression is the elasticity. We'll see this soon in lectures. Okay, I'm going to stop sharing this and I'm going to start sharing Stata. Okay, Stata. Hello. Now, I think a problem that happened on Friday was that Stata was demonstrated, but you couldn't see the graphs and the other windows that were coming up. This is what I thought. So this is what I could see when I looked at the recording. So I'm just going to make sure that you've got all this. Now, what we do first is we type in the data. Okay, so you go to Data Editor, and then in Data Editor, you type in the numbers. The first column is X and the second column is Y. Now, notice what's happened here. We filled in two columns, and over here we have two variable names. The variable names are var1 and var2. If we want to change the variable names, we can. I'm going to change var1 to X because that's what it's called in the question, and I'm going to put a label in. The label is income. Oh, sorry. Put it in the wrong place. Don't want it there. Income. Okay, and then I'm going to change the name of Y, so change the name of var2 to Y, and I'm going to put a label in here, which is food expenditure. Okay, so we've got the data, and we've got the name, variable names, and we've got the labels, so we can leave the data editor. Now we go back to the main Stata windows, and notice that we've now got over here in the variables window, we've got a list of the variables that are in memory. And if you use the command list, then you see that's a nice easy way of seeing the variables that you have in memory. List. Now, obviously, one of the important things is the scatter plot. So if we do scatter y x, now when you're doing a scatter plot, as I keep telling you, the variable on the y-axis is the dependent variable. So that's the variable that we call in y. The variable that's on the y-axis has to go first in the command. So scatter y(x), not scatter xy. The first one takes a few seconds. First time when you first go into Stata, the first graph takes a few seconds. This is the scatter plot that you get. Now, something you want to do is you want to make the origin of the graph 0, 0. This doesn't look good because the origin of the graph is 120. We want to make the origin 0, 0. How do we do that? Well, we make this axis go from 0 to 500. We make this axis go from 0 to around number 100. So how do you do that? You take the scatter command and you go x label 0, 100, 600, y label 0, 20, 100. See what that looks like. Right, now the origin is now 0, 0, so we can get a much better idea of what the relationship is between the variables. Notice this command here, these options in the scatter command tell us basically what the range of the x-axis is going to be, 0 to 600, with tick marks every 100. Y-axis, 0 to 100 with tick marks every 20. So there's our scatter plot, and as you can see, it's a positive relationship and it looks linear. How do we also draw a fitted line in this scatter? Well, you can do that in the scatter command. What this is actually adding another command to the scatter command. And the way you do this is you have two vertical lines. That just means there's another command, and we have the command lfit y(x). This is for the fitted line. Let's see what happens if we do that. There. Now that's the fitted line, but notice it starts there and ends there. We really want it to come down here so we can see what the intercept is. And if we could make it go up there so we can predict outside the range of the data. Well, the way you do that is you have an option for this command, and the option is range 0, 600. That says we want a fitted line that goes from 0 to 600 on the x-axis. So that's how you do a fitted line. And by the way, all the commands that we're using are in the Stata command sheet, which is now on the Blackboard site. So you'll find this command maybe on the second page of that document. So that's the scatter, that's the fitted line. The next thing we want to do is we want to find the estimate and the slope. And in order to do that, we use the regress command. Regress y on x. And the first variable is the dependent variable. The second variable is the explanatory variable. So when you do the regress command, you get your estimates. Now notice the estimates we see here in the table, but we get quite a lot of output here, but the most important things are in the table at the end, because the first column of this table is the coefficients. This is the point estimates. That's the slope estimate. That's the intercept estimate. And then here we have the standard errors, which notice these numbers are the same as the numbers we've talked about earlier that we worked out using a hand calculator. And here we have the t ratios. Now notice that the t statistics or t ratios are the coefficient divided by the standard error. So 0.14 divided by 0.0304 is 4.59. That column divided by that column is that column. These are the t statistics. Then we have the p-values. Now the p-value is the probability of getting a more extreme value than the one that we have. Remember, the p-value tells you how strong the evidence is that food is a normal good. And that's strong evidence. However, there's just one thing here. This is what we call a two-tailed p-value. What we want is a one-tailed p-value because we're doing one-tailed tests because we have a prior belief. To turn the two-tailed p-value into a one-tailed p-value, you have to divide it by 2. So the p-value for this test is 0.002, and that represents strong evidence. We have strong evidence that food is a normal good because p-value is less than 0.01. This p-value, when we've got a prior that this is positive, so we can divide by 2, 0.044. Well, that's less than 0.05, so we have evidence that food is a necessity, but it's not strong evidence. Why don't we have strong? Obviously, food is a necessity. Why isn't it strong evidence? Because we've only got 8 observations. If we had, and notice the sample size is there. If we had 800 observations, we would almost surely have a significant intercept as well as a significant slope. Then we have the confidence interval. Well, the confidence interval we worked out earlier, and we've got the same thing there. That's the lower and upper bound to the confidence interval for the slope and for the intercept. And what else have we got here? F statistic, R squared, we don't know about them yet. Root MSE, that's the thing that we call sigma hat. Where does that come from? That comes from the residual sum of squares. Notice the number you see here is the residual sum of squares. There are 2 other sums of squares, which I'll talk about very soon. The degrees of freedom for that sum of squares is 6. That's n minus 2. That's the thing that you need to divide by to get the mean squared error, which is 97.66. That's sigma hat squared. When you take the square root of that number, you get this number here, which is sigma hat, which is the number that's used to work out the standard errors. Now, obviously, all the calculations we did to get all these numbers, you don't need to do them if you've got Stata because you use the regress command. A question? Fire away.
Okay, good morning.
Good morning.
I'm sorry, I was a little bit confused on why you have to divide your p-value over 2, the probability value of the x variables. Why do you have to divide it by 2?
Okay, thanks for the question. I'll answer that in 2 seconds. I've finished talking about, I've said everything I want to say about Stata. So I'm going to stop sharing the Stata screen. But you know, I just have to check with you. I just have to make sure. When I showed you the graphs then, did you see the graph? Okay. Thank goodness you saw the graph. So look, we understand. Thank you. We understand now. I mean, I understand now what we need to do in order for you to see everything we do in Stata. So from now on, the workshops will run smoothly. I promise you. Okay. I'm now going to share. All right. Now, just going back to this. A good is a normal good. The question was about one-tailed and two-tailed. I understand this might be confusing. A good is normal if its angle curve has a positive slope. In other words, if beta 2 is positive, the slope of the angle curve, if the slope of the angle curve is positive, that's beta 2, then the good is a normal good, because this is food expenditure and this is income. So, and we have a prior belief that food is a normal good. So when we do our statistical test, all we want to do is confirm our prior belief. Is food, are we right to assume that food is a normal good? That's what we're testing here. So we're testing the null hypothesis that income has no effect on food expenditure against the alternative hypothesis that income has a positive effect. So the null is that income has no effect, and the alternative is that food is a normal good. Now, when we do the test, we work out the test statistic, and then we compare the, and we ask the question, does this number look like it comes from a T6 distribution, or is it in the tails? Because we're doing a one-tailed test, we only use the upper tail, one tail greater than test. We use the upper tail of the T distribution. If our number, which is here, is in the upper tail of the distribution, then we say we have evidence to reject the null in favor of the alternative. We have evidence that food is a normal good. Well, that's exactly what we have, because our statistic is here, 4.59. 4.59 is here. So we reject the null. We've got evidence that food is a normal good. Right, now I haven't got to the important part yet. The question was about p-values. The next question, we've agreed. We agree that we're rejecting the null in favor of the alternative. The next question is, how strong is the evidence that food is a normal good? How strong is the evidence? Is it mild evidence? Is it just average evidence? Is it strong? Is it overwhelming? How strong is the evidence? In order to answer this, we're asking the question, how far is this number into the tail? Is it just this side of the tail, or is it further in, or is it a long way out into the tail? Well, it's quite a long way out, but how do we quantify that? We quantify it by finding the p-value, which is the area to the right of this number. The area to the right, it's the probability of getting an even more extreme value. And this area here, this darkly shaded area here, is actually 0.002. Now in Stata, when you do all this in Stata as we just did, the number that you see there in that p-value column is not 0.002, it's 0.004, because Stata gives you two-tailed p-values. Stata will always give you the two-tailed p-value. And the two-tailed p-value is, when you're doing a two-tailed test, a more extreme value than the one you have implies a value greater than 4.59 or less than minus 4.59. In other words, when you're doing a two-tailed test, if you don't have a prior belief, then your p-value is worked out using both tails of the distribution. So the p-value that you see in Stata is 0.004. We are doing a one-tailed test because we have this prior belief. So we are only looking at the upper tail, and that's why our p-value is 0.002. That's why we divide by 2 when we have a prior belief, when we're doing a one-tailed test. Okay, I hope that's clearer. But we'll see more examples of this in the coming weeks.
It's clear now. Thank you.
Okay, that's good. P greater than 0. Now, P is always greater than 0. P is always a probability. It's always between 0 and 1, the P-value. And what you're looking for is a low P-value. If the P-value is less than 0.10, then it's mild evidence. Less than 0.05 evidence, less than 0.01 strong evidence. Okay, remember these are important. P-values. If the p-value is less than 0.10, that's 10%, that's mild evidence. You reject, you've got mild evidence against the null in favor of the alternative. Less than 0.05, this is the standard one, then you just say there's evidence. It's not mild, it's not strong, it's just evidence. And if the p-value is less than 0.01, 1 in 100, then you say there is strong evidence. Okay, so be careful with these numbers. If you have a very large p-value, then that means the variable's not significant at all. It means there's no effect. You want a low p-value. A low p-value tells you there's something going on. All right. I hope that's useful. As I've just told you, or as I told you earlier, workshop 3 is the same thing. All right. Now, all the workshop material is now on the Blackboard site. So you may not have seen this yet, but it's on the Blackboard site. This is the workshop for this week. More practice with simple regression with and without stata, also to linearity. Question 1 should be answered without using a computer package, and your answer should be brought to the workshop in week 3. Okay, so I'm telling you to use one of these. All right, use one of these to work out the answers. The following table contains data on 10 rental properties advertised in the window of Abbott's estate agent Norwich on 4th September 2021. Number of bedrooms is X, 0, 0, 1, 1, up to 4. This is real data, by the way. And Y is rent in pounds per month. So what are we doing here? Well, we're doing something very similar to the food example, but not the same. Number of bedrooms in the property and rent of the property. The first property has no bedrooms and rent 620. You'll find that the data looks something like this. Starts at 0. Again, the problem is to draw a straight line, or fit a straight line through the data, and to interpret the intercept and the slope. Now, just one thing, don't start talking about normal goods and necessities. It's not normal, this is not income, it's number of bedrooms. So get out of the mindset of normal goods and inferior goods and necessities and luxuries. It's not about that. That's only if you've got consumption of a good and income. What we have here is number of bedrooms and rent. And we're interested in, well, you work out what we're interested in here. Again, you start by plotting the data, and then you find the estimates of the intercept and the slope, and then you do a prediction. Then you find the residuals. Which property has the highest positive residual? Think about this. If you do your regression and you find a house or a property has a very high negative residual, what does that mean? What does that tell you about this property? Think about that. That could be very useful for you if you're looking for a property in Norwich. And then we find the standard error, and then we do a test, and then we go a bit further with this. When you do the scatter, you might find when you ask one of the first questions is it linear? Is it a straight line? Well, you might find that it's not a straight line. You might find it looks like a curve. So then we have to ask the question, why do we think it's curved, and how do you deal with the curve in your model? If it's a curve, then obviously this equation is no longer valid. We need something else. We need something a bit more complicated if we want to capture the curve. So that's what this exercise is. Do your best with it, and we'll compare answers on Friday, and we'll do it in stata as well. And we'll compare the stata answers with the answers that you get using a calculator. That's workshop week 3. Okay, now I'm going to get on with the lecture now. This is page 18 of the lecture notes. The effect of changing units of measurement. Well, this is quite an important point, because basically when you look at the coefficients, where do you find the workshop questions? In teaching, what's it called? Learning resources, or I always forget what it's called. There's a folder in the Blackboard site, not in this Blackboard site because we're on the dissertation Blackboard site now, but the Blackboard site for your module, in the folder where all the material is, you will find the workshop, learning materials, thanks a lot. You'll find a document containing all of the workshop material for the first 7 weeks. Okay, now when you look at the coefficients, sometimes you see a very small number, like 0.00003, and it's tempting to say this slope is very small, so it's irrelevant. But that's wrong, because the magnitude of a coefficient depends on the units in which you measure the variable. So let x be income in pounds. This is just to demonstrate. Consider what happens if we switch to measuring income in pence. So x star is income in pence, x star is 100 times x. What does the slope estimator become? If we put x star in place of x everywhere in the formula, y stays the same, then what we're doing is we're multiplying by 100 here, and we're multiplying by 100 here, but because there's a square there, we end up by dividing by 100. So what happens is, if you use pence instead of pounds, then the slope estimate becomes 100 times smaller, right? So if you want to make your slope smaller, you just use different units of measurement. What happens to the standard error? The standard error is given by this formula here. And if we use pence instead of pounds, similar thing happens to there. We get 100 squared here, but we've got it's inside a square root. So we're basically dividing by 100 from what we had before. So when you use pence instead of pounds, the coefficient, the slope estimate becomes 100 times smaller, and the standard error becomes 100 times smaller as well. What happens to the t ratio? Well, remember the t ratio is the estimate divided by the standard error. If they both become 100 times smaller, then the t ratio does not change. The t ratio for testing the significance of the effect of a variable is invariant to the units of measurement of the variable. The t ratio is the same whether we measure income in pence or pounds. It's the same whether we measure weight in kilograms or grams. You know, the t ratio is always the same, and the t ratio is the important thing because that tells us whether the variable is important. So the point here is here. In many situations, the magnitude of the coefficient estimate is not important since it depends on the units of measurement. The associated t ratio is always important. Now, there's another minor point here. When reading stata output, you need to understand exponential notation. What are the following numbers? 3.74e minus 06. What is that? That is not 3.74. It's 3.74 with the decimal point shifted 6 positions to the left. To the left because that's a minus. So this is, take your numbers that you start with, and the decimal point starts there, but we're shifting it 6 positions to the left. 1, 2, 3, 4, 5, 6. So the decimal point is here, and you have to fill in some zeros here. So what we've got here is decimal point, 50374. So that's a very small number. Now sometimes you see that in the first column. I just want to make sure you know what it means. This is exponential notation. The number e minus 06, that means move the decimal point that many places to the left. What about this one? 3.74e plus 06. This means move the decimal point 6 places to the right. So 1, 2, 3, 4, 5, 6. That's the number. Now, then that's a very large number. That is 3 million. Now, with large numbers, it's conventional to put commas every 3. So 3,740,000. Now, if you come from some countries in the world, right, the way we write this number is 3,740,000 point, decimal point, 00. Okay, now if you're from certain other countries in the world, then you might write that number as 3.740.000, comma 00. That's fine. If that's your convention, then you're welcome to use that convention. But I just want you to let you know that this is the convention that we use. Commas separating groups of 3 digits, and then a dot for the decimal point. After all, it is called a decimal point, isn't it? Watch this number here. Well, here there's a minus sign before the number. So, well, these two numbers are both positive numbers. All that's happening here is that we've got a negative number, which is the same as this number here. So it's minus 0.0000, 5 zeros and then 374. Right, that's large and small numbers, and the notation that we use for large and small numbers. In fact, let's see. I think it would be that key, this key here. On the calculator. The key that we're talking about is the times 10 to the x key. And that's how you would input the number into your calculator. Anyway, let's move on. That's page 18 of the lecture notes. Page 19, linearity. An equation must be linear in the parameters for ordinary least squares to be possible. It does not have to be linear in the variables. Examples. See also workshop 3, question 3. So that's the workshop this week. We've got a question on these. Now, remember that beta 1 and beta 2 are always parameters, while x and y are variables. So the model that we've been considering so far is the simple regression model, which looks like this. Y is beta 1 plus beta 2, x plus u. This is linear in parameters and variables. It's linear in parameters because it's on the right we have a parameter plus a parameter times something plus something else. So it's linear in parameters. So obviously we know that we can estimate this model by ordinary least squares. And that's what we're interested in here because it's linear in the parameters. This model here, y equals beta 1 plus beta 2, 1 over x, is linear in parameters because it's beta is a parameter plus a parameter times something. It's non-linear in variables because the thing you see here is not x, it's 1 over x, or the reciprocal of x. And this is often called the reciprocal model because it's the reciprocal of x. Now, all you'd have to do here is you'd have to generate a new variable, which is 1 over x, or the reciprocal of x. Generate a new variable, then do a regression with your new variable, and you would get estimates of beta 1 and beta 2. There's the link to the QR code. Yes, we'll see applications of that model. Now, what about this one here? Y is beta 1 x to the power beta 2 plus u. This model is non-linear in the parameters because look, it's beta 1 times something to the power. It's a parameter times something to the power another parameter. It's non-linear in the parameters. So you cannot estimate this model by least squares. If you want to estimate this model, you can do. If you want to estimate beta 1, beta 2, then you have to use something called non-linear least squares, which is minimize S equals, I mean, it's just like least squares. It's just the thing that we're minimizing is the sum over the sample of y minus beta 1 x to the power beta 2 squared, and put i's on there to make it clear. Sum over I, yi minus beta 1 xi to the beta 2 squared. That's non-linear least squares problem, because what we are doing with ordinary least squares is we have something here which is linear in beta. And we differentiated this. We got two equations, and we said, we didn't do it, but we said if you solve these two equations, then you get the formulae for that we use for ordinary least squares. If you try to do that for this, if you try to differentiate this with respect to beta 1 and with respect to beta 2, set them equal to 0 and solve, you won't be able to. You won't be able to solve those equations. So it's a non-linear problem, and you can only solve it numerically. There's not an analytical solution, there is a numerical solution. In other words, you try different combinations of beta 1 and beta 2 until you get to the lowest value of S. And that's how you get estimates, but that's not too important. The important thing is, because this is non-linear in the parameters, we can't use ordinary least squares to estimate those parameters. What about this one here? This is similar to that, but it's not the same. The difference is there we have plus u, plus error term. Here we have times error term. This is non-linear in parameters. However, if you take the logs of both sides then and use the rules of logarithms, then you get log of y equals log of beta 1 plus beta 2 log of x plus log of u. And notice all we're doing here is using the rules of logarithms, that when you take the log of a product, you get a sum. When you take the log of a power, the power becomes a multiplicative coefficient. So we're using the rules of logarithms to get to here. Now this can be written differently. If we say that log beta 1 is just beta 1 star and log u is u star, then we have something that looks very like a linear regression. And this is linear in the parameters. It's linear in the parameters beta 1 star and beta 2. So you can estimate these parameters using ordinary least squares. So this is quite important. When you start off with something like this that looks highly nonlinear, you've got to think, can you transform it into something that is linear? And the answer is yes. You take the log of both sides and you get something called the double log model. That's the double log model because it's got logs on both sides. Page 20. I'll just carry on for a minute or two. The alternative functional forms. The food model was essentially this model here, beta 1 plus beta 2x, y equals beta 1 plus beta 2x. There was an error term as well, but let's just consider the deterministic part, the theoretical component of this model. Recall the interpretation of the slope parameter. When income rises by £1, food expenditure is predicted to rise by beta 2 pounds. That's the interpretation of the slope in this model. What is income elasticity of demand? The general formula for the income elasticity is, call it eta. This is the Greek letter eta. It's dy over y divided by dx over x. Because remember, an elasticity is a proportional change divided by a proportional change. Dy over y is like the change in y as a proportion of y. Dx over x is the change in x as a proportion of x. If you take the ratio of those two proportional changes, then you have the thing that we call the income elasticity. And if you rearrange this, you can write it as dy by dx, which is the slope of this. And you have times, and the x, because it's the denominator is divided by x, the x goes there, and the y goes there. Applying this formula to model 1, what do we have? We have elasticity equals dy by dx, which is just beta 2, differentiating a straight line, you get the slope, times x divided by y, and for y we use what's on the right hand side here. So this is the elasticity, income elasticity of demand for food. Now we can simplify this because we can put the beta 2 there. Notice that's not an x, it's a times symbol. What's the difference between an x and a times symbol? The times symbol is symmetric. The x symbol for x is not symmetric. That's a very small point. So the income elasticity of demand for food is beta 2x over beta 1 plus beta 2x. So I'll make this the final point, and then I'll carry on tomorrow. We see that the value of income elasticity depends crucially on the sign of the intercept. The intercept is beta 1. The income elasticity is this thing here, but you can see if beta 1 disappears, then you have 1, because the top is the same as the bottom. So if beta 1 happens to be 0, then the income elasticity is 1. If the intercept, if beta 1 is positive, then the denominator is larger than the numerator. Therefore, the income elasticity is less than 1. And the demand for food is income inelastic. And Engel's law holds. This is another way of looking at Engel's law. Engel's law says that the income elasticity of demand for food is less than 1. If beta 1 equals 0, then the top and bottom are the same, and elasticity, income elasticity is 1, and food expenditure rises in proportion with income. If beta 1 is less than 0, then the top is greater than the bottom, so the ratio is greater than 1, elasticity is greater than 1, and food demand is income elastic. So this is quite useful because it shows us that the important parameter here is beta 1. The sign of beta 1 tells, in this model, the simple regression model, the sign of the intercept tells you whether the good you're looking at, whatever it is income elastic or income inelastic. But remember, this is only in the context of a model in which X is income and Y is expenditure on a particular good. Okay, I'll stop there. But I'll stay around in case there are any questions. I'll see you again tomorrow afternoon at 2 p.m.